Hello, beta. Good morning, everyone.
Good morning, sir.
Good morning. Okay, the recording of the meeting is on now. So today we will be discussing about number one, circumpolar bodies. And once we finish that, we will be moving on to principles of navigation based questions, actual numerical questions which come in our papers. So that consists of different topics. Beta, do you get a lot of background noise? Are you getting it, or is it okay?
We are getting.
Okay, just give me 1 minute then. How is the background noise now? You still get a lot of disturbance, or is it better?
Hammering sound is still there.
Okay, too much disturbing?
नहीं सर ठीक है सर.
Okay, all right. I have put the noise suppression on. Anyway, so this is the plan. So first I'll start off the circumpolar bodies with you. So shall we go into the presentation, beta?
Yes, sir.
Okay, great. Just give me 1 minute. I'll set up. In this presentation, we are going to learn about circumpolar bodies. The literal meaning of the word circumpolar is making circles around the pole. Now, fundamentally speaking, all the celestial bodies, they move in circles around the pole. All the celestial bodies move on their declination circles, and all these declination circles are centered at the pole only. But as far as the circumpolar term is concerned, we call those bodies as circumpolar whose circular motion is visible to us. The complete circular motion around the pole is visible to us. In other words, a body is said to be circumpolar if the body is always above the rational horizon of the observer. That is, the body should not set. During the full day, the body should not set. These type of bodies are called as circumpolar bodies. They remain above the horizon of the observer, and you are able to visualize or you are able to see them at any time of the day for full 24 hours. Now, let's try to understand when does a body become circumpolar, or what are the conditions which lead to a body becoming circumpolar. This can be easily understood from a rational horizon diagram. Now, let's assume that our observer is in northerly latitude in the north hemisphere. You can assume latitude close to 40 degrees north or so. And let's make a rational horizon diagram for the observer. We have the rational horizon. We mark off the NESW points on the rational horizon. Then we mark the celestial meridian of the observer. We mark the prime vertical circle. Exactly at the center of this diagram is the zenith of the observer, represented by Z. Now, since the observer is in the north hemisphere, the latitude is north, equinoctial will be passing south of the observer. So from point Z, if we go down south equal to our latitude, now that gives us the point from where the equinoctial will be passing. It is represented as point Q in the rational horizon diagram. We are aware that equinoctial always passes from west and east points. So now we know that the equinoctial will pass from W, Q, and E. And we can now show the equinoctial in our diagram. We have the equinoctial here. Now, once the equinoctial is there in the diagram, we can also show the pole. In this case, the observer is in north hemisphere, so the north celestial pole will be the elevated pole or the visible pole, and it will be 90° away from the equinoctial. So 90° away or 90° north of the Q point, this is where the pole would lie. So let's mark this point as P, representing the north celestial pole. Now in this diagram, let's assume some celestial bodies of different declinations and let us see whether they become circumpolar for this particular observer or not. Let us first assume a body with a declination opposite to the latitude. The latitude in this case is north, so let's assume a body having a southerly declination. Now in this diagram, we are aware that this N point is on the horizon. The P point represents the pole, and this N to P, what is highlighted by this yellow line, is called as the elevation of the pole or the altitude of the pole. And this is always equal to the latitude of the observer. We can easily understand it from the diagram. Now, the N point is 90° away from the Z point, from the zenith, because every point on the rational horizon is 90° away from the zenith of the observer. Similarly, the P point, which represents the pole, is 90° away from Q point, which is the equinoctial. So P to Q is 90 degrees, that is pole to equinoctial. N to Z is 90 degrees, that is rational horizon to zenith. So therefore, what is the arc ZQ? It will be exactly the same as arc NP. ZQ was the latitude of the observer, so NP, which is the altitude of the pole or elevation of the pole, will also be equal to the latitude of the observer. So let's now assume some celestial body. As I told you, first let's assume a body having a southerly declination. So we have a star here. You can see it is south of the equinoctial, having a southerly declination. Let's try to show the path of this star, the path on which this moves, that is the declination circle of this particular star. All the declination circles are parallel to the equinoctial. So the declination circle of this particular star, parallel to the equinoctial, would appear something like this. The declination circle shows us the path on which the body moves. Now this body is going to rise at this particular point on the horizon. You can follow the laser pointer on the screen. This is the point where the body is going to rise on the eastern horizon. After rising, it will move on its declination circle. It will cross the meridian of the observer at this particular point and then cross over to the western side. And eventually it will go and set at this particular point on the western horizon. And we can see here that this body is certainly not circumpolar, because at this particular point, it is going to go below the horizon of the observer. Now you could have picked up a body of any southerly declination lying between Q and S points, and you will see that all those bodies declination circle will hit the western horizon at some point, making that body go below the horizon. So any body with a declination opposite to the latitude will not be a circumpolar body. Beta, any doubt up to here?
No, sir.
Okay, great. Now let's see some other bodies with different declinations. So this is one thing which we have seen now. Now let's assume a second celestial body with its declination of the same name as latitude of the observer and see whether it becomes circumpolar or not. So you can see in the diagram, this is the rising point of the body. A body moves in this particular direction represented by the arrow and then eventually sets at this particular point. Now let's assume a second body here. Now this star is north of the equinoctial and the declination of the star is of the same name as the latitude of the observer. Let's try to show the declination circle of this particular star. The declination circle will pass through the body and it will be parallel to the equinoctial. So this is how the declination circle is going to appear. On this declination circle, the body will be moving in this particular direction represented by the arrow. The body will be rising at this particular point, moving in this particular direction, crossing the meridian here, and at this particular point, the body is going to set. So we saw that even this particular body is not circumpolar. So it is not necessary that with lat and dec of the same name, a body should certainly be circumpolar. Let's try to increase the declination a little bit now. Let's assume a third body, this particular star now. This is also having a northerly declination, but the declination is more than what we had in the previous case. Let's try to draw the declination circle of this particular star. Now declination circle will pass from the body and it will be parallel to the equinoctial. Now in this case, the declination circle is going to be like this. All the declination circles are centered at the pole. So centered at the pole, polar distance equal to px, pole and the body. If you draw a circle, that gives you the declination circle of this particular star. Now the arrows show the direction in which the star will be moving on this particular circle. Now we can clearly see that the entire declination circle of this particular star is above the horizon of the observer. It touches the horizon at the north point, but never goes below the horizon. So these bodies which remain above the horizon of the observer for full 24 hours and never set are circumpolar bodies. So one thing we have seen from this diagram that it is certainly not possible to have a body circumpolar with lat and dec for opposite names. So one condition which we can pick up from this rational horizon diagram is that for a body to be circumpolar, the first condition is the latitude and declination. Latitude of the observer and declination of the body should be of the same names. Any doubts up to here, beta?
No, sir.
Okay, great. Let's continue. Now in this diagram, I have also shown the polar distance of the body, P to X. This represents the polar distance of this circumpolar star. and it is always equal to 90 minus declination. So polar distance in this case, which is 90 minus declination, is shown in the diagram. Now we can clearly see in this particular diagram that for a particular body to be circumpolar, the polar distance of the body, which represents the radius of the declination circle, should always be less than or equal to np. If the polar distance is more than np, then you can clearly see from the diagram that the declination circle will go beyond the horizon of the observer. It will go below the horizon of the observer, making the body not a circumpolar body. If it has to be circumpolar, the radius of this circle, that is px, should be equal to or less than np. If the radius is equal to np, you will have exactly this particular condition. The circle will be touching the horizon at point n. And if the radius is less than np, then the entire circle will be within the rational horizon of the observer. So we understand from this diagram now that for a body to be circumpolar, this condition should be met. That is, the polar distance of the body should be equal to or less than the elevation of the pole, or NP. Now, NP, or elevation of the pole, is equal to the latitude of the observer. So we now come to this relationship that Px, which is the polar distance, should be less than or equal to Np, which is the latitude. Now, polar distance is equal to 90 minus declination. So this converts the relationship into 90 minus declination should be less than or equal to the latitude of the observer. Now, if I take declination to the other side, to the right-hand side, the relationship becomes latitude plus declination should be greater than or equal to 90 degrees. So this is the second condition which needs to be fulfilled for a body to become circumpolar. The first condition which we saw in the previous slide was that the latitude and declination should be of the same names. The condition which we saw in this particular diagram is latitude plus declination should be greater than or equal to 90. So these are the two conditions which needs to be met for a body to become circumpolar. Beta, any doubts up to here anywhere?
No, sir.
Okay,
Sir?
great. बोलो बेटा.
सर एक नॉर्मल सी डाउट थी कि नॉर्मली हम लोग बोलते हैं कि जब रेशनल होराइजन के ऊपर बॉडी आती है तो फिर वो राइज हो गई और रेशनल के नीचे जाती है तो सेट हो गई. बट सर हम जो भी बॉडी रहती है उसको तो हम अपने विजुअल होराइजन से ही देख पाते हैं, तो फिर ऐसा मतलब कन्वेंशन क्यों किया गया?
Okay, all right बेटा. Now बेटा, you are right, because हम जो horizon को देखते हैं वो visible horizon होती है और हमारी rising और setting is with respect to the visible horizon. But इस diagram में हम consider करते हैं rational horizon को. So why this difference? उसका reason ये है बेटा कि visible horizon जो है, it is dependent on the height of eye of the observer. It is something which is variable. If your height of eye increases, the visible horizon will also change. Height of eye decreases, visible horizon again going to change. So it is difficult to show the visible horizon in this particular diagram. So that is why we do not make the diagram basis the visible horizon. We always make it standardized basis the rational horizon of the observer. And the difference between both of them is so less that it does not create a substantial error or difference in our answers. So that is how we are able to manage it. Is it clear now, beta?
Yes, sir.
Okay, all right. So shall we move further now?
Yes, sir.
Okay. Latitude and declination same names, and latitude plus declination greater than or equal to 90 degrees. So remember these two conditions for a body to become circumpolar. Now going a little more deeper into the circumpolar bodies, we had this particular star, and the polar distance is less than or equal to NP in this case. And you can see the entire declination circle of the star is within the rational horizon of the observer. So this is a circumpolar star. Now, the direction of this, the motion of the star is represented by these two arrows. Now, in this particular diagram, we can see that the star comes north of the observer at two instances. At point A here, it will be north of the observer. The bearing of the star would be 0, 0, 0. And again, when it reaches or crosses the meridian at point B, it will be again north of the observer with a bearing 0, 0, 0. Now, this is only possible in case of a circumpolar body. For a normal body which is not circumpolar, it will come north or south of you, or in other words, you can say it will come on your meridian only once in a day. But a circumpolar body will be north or south of you twice in a day. Roughly after an interval of 12 hours, it will be south or north of the observer two times in a day. Now, both of these instances are called as meridian passages. Uh, One of them is the meridian passage on the observer meridian. If you look carefully in the diagram, P is the pole and P, Z, Q, S is the observer's meridian. And you can see that at point B, the body crosses the meridian of the observer. Now, at the second instant, that is at point A, it is crossing the inferior meridian of the observer, or the opposite meridian of the observer. You see, when you go on other side of the pole, this represents your inferior meridian, reciprocal meridian. So at point A, the body crosses the inferior meridian of the observer. At point B, it crosses the meridian or the observer's meridian. Now, point A is known as meridian passage on the inferior meridian. You can call it the meridian passage of the body on the inferior meridian, or you can also call it meridian passage below the pole. Now, why do we call it meridian passage below the pole? That also can be seen easily from this diagram. We know N to P is the elevation of the pole or the altitude of the pole. So N to P represents the elevation or altitude of the pole. N to A represents the elevation or altitude of the body at the time of meridian passage on the inferior meridian. And we can clearly see that the altitude of the body is lesser than the altitude of the pole. That is why at this particular instant, that is at point A, the meridian passage of the body occurs below the pole. Now, this is for this particular reason, this is also called as lower meridian passage or lower Marpas. At the same time, the point B, which you see, is known as the meridian passage on the observer's meridian. Point B represents the meridian passage on the observer's meridian. It is also called as meridian passage above the pole, because you can see at this point the altitude of the body is represented by NB, November Bravo. The altitude of the pole is NP, November Papa, and the altitude of the pole is less than the altitude of the body. The body is at a higher altitude at point P. So that is why it is called as meridian passage above the pole. And it is also known as upper Marpas or upper meridian passage, because at point B the body is above the pole. It is at a upper location than the pole. So upper Marpas and the lower Marpas. Upper Marpas or meridian passage above the pole is on the observer's meridian. Lower Marpas or meridian passage below the pole is on the observer's inferior meridian. Now, if you remember, when you look for the meridian passage time of the moon in the almanac, there are two times which are given, one under upper and other under lower. This upper and lower basically means the meridian passage of the moon on the observer's meridian, that is for upper, and for lower, it is the meridian passage of the moon on the observer's inferior meridian.
Beta, just give me 1 minute. Okay, let's continue.
Let's now practice a numerical question based on the concept of circumpolar bodies.
Beta, before we go into the numerical, any doubts up to here?
सर वो लास्ट स्लाइड एक बार दिखाना प्लीज.
The upper and lower Marpas?
Yes sir.
Okay, beta. This is the one, beta.
Okay sir, thank you.
Okay. Shall we move on to the numerical now?
Yes sir.
Okay.
Let's now practice a numerical question based on the concept of circumpolar bodies. We have the basic understanding of the circumpolar bodies now. So let's go into this question. The question says, to a stationary observer, an unknown star bore 000 true with a true altitude of 78 degrees 12 minutes. After about 12 hours, the same star bore 180 true with a true altitude of 18 degrees 54 minutes. We have to calculate the observer's latitude and the star's declination. So a very straightforward and simple looking question. You observe here in this question that the star is bearing 000 at a particular time, and after about 12 hours it is again bearing 180. So at one time it was north, at other time it was south. So this is only possible in case of a circumpolar body. Otherwise, for bodies which are not circumpolar, they come north or south of the observer only once in 24 hours. Anyway, let's now try to see how do we solve these type of questions. Now, all circumpolar questions can be solved using a single approach. If you have that approach clear in your mind, you will be able to attempt any question based on circumpolar bodies. Not only circumpolar bodies, later on we will also see the questions based on rational horizon diagram, and the same approach is applicable to those questions also. So what is this approach with which we can solve these questions? The approach is that in all these questions, you make a rational horizon diagram. Make a rational horizon diagram, and whatever information is given to you in the question, a true altitude or a bearing, whatever is given to you, try to put all that information in that rational horizon diagram itself. Now, when you put all the information, what was given in the question, in the rational horizon diagram, the diagram itself will give you a lead into solving the question. For circumpolar bodies, you will not even need to use a formula. No formula is required. Only by adding or subtracting, you will be able to find your answer. But in other rational horizon question, once you put all the information in the diagram, you will be able to solve it by a spherical trigonometry formula. A pz-x triangle is formed, and you are able to solve it using either the cosine formula or the Napier's rule. So let us apply this approach in this particular question and see how it works. Let's draw the rational horizon of the observer. Let's mark off the NESW points. And at the center of this diagram, we have the zenith represented by Z exactly in the center of this diagram. So let's try to put the information now what is given to us. The star is bearing 0, 0, 0 with a true altitude of 78 degrees 12 minutes. Now in this diagram, the 0, 0, 0 bearing or north bearing is represented by line NZ. Line NZ represents the north bearing or 0, 0, 0 bearing. So the star has to be somewhere on this line. Now point N being on the horizon is at 0 degree altitude. Point Z being the zenith of the observer is at 90 degree altitude. The altitude which we require is 7812. So from the horizon going 7812, somewhere here is going to be our star. So let's mark off this altitude in green. You can see the green color line on the plot now representing altitude of 7812. And this is where we have the star. So unknown star is bearing 0, 0, 0, and it is at a true altitude of 7812. Now after about 12 hours, the same star bore 180 true. Now 180 bearing is represented by line ZS, and on this line we have to mark a true altitude of 1854. S is the horizon, 0 degree altitude. Z is the zenith, 90 degree altitude. So from the horizon, we move 18 degrees 54 minutes up. From the horizon, we move 18 degrees 54 minutes up, and this is where our star is. So let's mark off the star here. You can name this location as Y. The initial location where the star was bearing north is named as X, and at southerly bearing the star is named as Y.
Beta, up to here, any doubts?
No, sir.
Okay, great.
So you have all the information what was given in the question in the diagram now. Now these X and Y indicate the location of the same star. Now if the star is at X location at one point of time, and after about 12 hours it is at Y location, that means the declination circle of the star has to be such that it passes from both X and Y. The declination circle should be such that it passes from both these points X and Y. Now there is only one possibility of how the declination circle is going to be, and that possibility is the declination circle passing from both the locations in this way. There is no other circle which you can draw in this diagram so that point X and point Y lie on that same circle.
So is this part clear, beta?
Yes, sir.
Okay, very good.
So this is the only possibility of the declination circle of the star. So you see, once we have position X and Y known to us, we can easily make the declination circle of the star. So this is the approach. Now, from the declination circle, now we can also identify the pole. We are aware that all the declination circles are centered at the pole. Now we have the declination circle of this particular star. So that tells us that at the center of this circle will be the pole. So let us draw the pole. It will be at the center of this particular circle. The center is going to be here. So let's mark the center of this circle. This is where the center is. And let's mark this as point P. So we have the pole in our diagram now as the center of the circle. And we can also mark off the direction in which the star is moving in this circle. These green arrows, they represent the direction in which the star will be moving. All the celestial bodies, they rise on the eastern horizon. They go up to the meridian of the observer and they set on the western horizon. So this is the direction in which the bodies appear to move. So we have the center at the pole, center of the declination circle. Now moving further, you see the distance n to x is 78 degree 12 minutes and the distance s to y is 1854 minutes. Now we know that from s to z is 90 degrees and from z to n is also 90 degrees. So total distance from n to s is 180. The diameter of this diagram, the rational horizon diagram, is 180. If n to s is 180, we know nx 7812 and we know sy 1854. Then in that case, we can easily find out this particular distance, that is from x to y. It will be 180 minus 1854 minus 7812. So xy in this case comes to 82 degrees and 54 minutes. So xy is 82 degrees and 54 minutes. Now this xy is the diameter of the declination circle. If you divide it by 2, you will get the radius of this declination circle. So 8254 divided by 2 gives you 4127. So this 4127 is the radius of this circle, which is equal to px or py. So polar distance of the star P to X is the radius of this declination circle. Once the pole is there in the diagram, we can also mark off the equinoctial. The point Q of the equinoctial is 90 degrees away from the pole. So we have the pole here. 90 degree away from the pole is this point Q on the equinoctial. And we know equinoctial always passes from east and west points. So joining W, Q, and E, we can mark off the equinoctial in our diagram. Now we know the polar distance Px, we have calculated it as half the diameter. It is 4127. From this, we can now find out the declination of the star, which is basically how far away from the equinoctial this star is, that is Q to X. And this declination is equal to 90 minus polar distance. You can see P to Q is 90, P to X is 4127, that is the polar distance. So Q to X will be 90 minus 4127, that is 48 degree 33 minutes. So Qx, which is the declination of the star, is equal to 48:33 minutes. And we can see in the diagram that the star is south of the equinoctial, so the declination is south.
सर क्यों XY 82 कैसे आया सर, एक बार बता देंगे फिर से?
Okay.
XY
Beta,
82.
yeah, right. I'll tell you. From point N to point S, this total is 180 degrees, right?
Sir, yes.
हमने 180 में से जो ग्रीन कलर की NX आर्क है 78 इसे माइनस कर दिया
18 डिग्री 54 माइनस कर दिया, ठीक है।
और SY 1854 को भी माइनस कर दिया and we got the diameter of the circle. Okay? Okay. और बेटा और कोई डाउट अभी तक?
नहीं सर।
Okay, very good. So you see we have obtained the declination of the star. Now the thing which remains is the latitude of the observer. So let's see that also. Just give me 1 minute.
What 48:33 south. So this was one of the items which was required. The star's declination has been obtained as 48:33 south. Let's move ahead now. We have the declination. The next thing which we need to find is the latitude of the observer. Now finding the latitude is easy. In this particular diagram, the latitude is represented by ZQ. Z is the zenith, Q is the equinoctial. So ZQ represents the latitude of the observer. And this is equal to PS or SP. SP or PS is the elevation of the pole or the altitude of the pole. And we are aware that the elevation of the pole is always equal to the latitude of the observer. So if we find out the value of PS, it will give us the latitude. Now PS is easy to find. PS is basically equal to SY plus PY. SY is given as 1854, that is the altitude of the star. So we know SY is 1854 and PY is nothing but the polar distance of the star, which we had already found out. So SY 1854 and PY is the polar distance which we already found was 4127. So when you add these two, SY plus PY gives you the elevation of the pole equal to the latitude of the observer, and it comes to 60 degrees 21 minute south. So both the required items have been obtained. The declination of the star is found and the latitude of the observer is also obtained.
So is it clear, beta? Any doubts?
सर ये जैसे इसमें तो आवर डिफरेंस दे रखा था 12 और 0, जैसे अपर मेरिडियन और इंफीरियर मेरिडियन तो सेम चीज यही होती है ना इसमें भी, कि ऊपर वाला अपर मेरिडियन हो गया और नीचे वाला इंफीरियर मेरिडियन हो गया क्वेश्चन में जो होता है.
I didn't get your question, beta. Can you repeat, please?
सर जैसे कुछ क्वेश्चंस में इसमें तो जैसे टाइम दे रखा था आफ्टर 12 आवर्स.
Right.
कुछ क्वेश्चंस में डायरेक्टली दो मेरिडियंस के 2 एल्टीट्यूड दे रखे होते हैं, अपर मेरिडियन एंड इंफीरियर मेरिडियन के, लोअर
Right.
मेरिडियन के. तो वो
Right.
सेम ही कंडीशन होती है ना कि अपर वाली तो ऊपर वाली हो गई विद रिस्पेक्ट टू द पोजीशन ऑफ द जेनिथ, और लोअर वाली जो नीचे वाली हो गई, यही होता है ना?
बिल्कुल बेटा, exactly, you are right. Whether they give you two meridian passage with an interval of 12 hours, or they tell you that upper Marpas, this was the altitude, lower Marpas, this was the altitude, it is similar question, exactly done in the same method.
ओके सर।
Okay.
हाँ सर, एक और डाउट पूछना था सर। ये अपना सर, ये अपना जब मून का आपने एक एग्जांपल दिया था, वहां पे मरपास में करेक्ट, वो अपर मरपास और लोअर मरपास का वैल्यू दिया रहता है। अगर
Right.
क्वेश्चन में एएम या पीएम दिया हो लैट बाय मेरिडियन में, तो उस कंडीशन में हम कौन सा वाला लेंगे? हमेशा लोअर मरपास वाला लेंगे?
नहीं बेटा, हमेशा अपर मरपास वाला लेना है आपने। मून के क्वेश्चन में जब भी कभी मरपास टाइम उठाना है तो हमेशा अपर मेरिडियन पैसेज टाइम को ही पिक करना है, बिकॉज अपर मरपास इज द मेरिडियन पैसेज ऑन द ऑब्जर्वर्स मेरिडियन। जैसे इस डायग्राम में आप देख रहे हो, जो पॉइंट एक्स है, पॉइंट एक्स, दिस शोज द अपर मरपास एंड इट इज ऑन द ऑब्जर्वर्स मेरिडियन। ऑब्जर्वर मेरिडियन इज PZQN। जो लोअर मरपास होता है उसे सिर्फ तभी लेना है अगर क्वेश्चन में बताया गया हो दैट दिस मेरिडियन पैसेज ऑफ द मून was on the inferior meridian of the observer. Only then lower, otherwise all questions upper.
सर सर
हाँ जी।
अगर उन्होंने ये लिखा हो कि जैसे एक्स मेरिडियन काउंट करना और उन्होंने बोला हो कि एएम टाइम पे हुआ है, और हम सर नॉटिकल अल्मनाक में देखते हैं जो लोकल मीन टाइम दिया रहता है मरपास का, तो उसमें जो मरपास का टाइमिंग मतलब 11 बजे के आसपास होगा वही वाला लेंगे ना?
बेटा पहली बात तो ये कि मून के मरपास का AM PM से कोई लेना देना नहीं है, तो AM PM जो भी इंडिकेशन उन्होंने दे रखी है उसे मून के साथ कनेक्ट नहीं किया जा सकता।
ओके।
सो आपने तो अपर मरपास का टाइम एल्मनैक से पिक करना है, और जो दो पॉसिबिलिटीज आपको क्रोनोमीटर टाइम की मिलेंगी, देखना है कि उनमें कौन सी पॉसिबिलिटी अपर मरपास टाइम के साथ मैच कर रही है, कौन सी क्लोज है, वही आपका एक्स मेरिडियन का टाइम है।
ओके
सर अगर इसी केस में रात इवनिंग को साइट ले रहे हो तो स्टिल मॉर्निंग का ही लेना है सर?
आई डिडंट गेट यू बेटा, कैन यू एक्सप्लेन प्लीज?
सर जैसे उसने बोला लोकल साइट हम एलएमटी निकालते हैं जब साइट का किसी एएम पीएम इंडिकेट दिया रहता है, पीएम रहता है साइट में, किसी भी क्वेश्चन में पीएम इंडिकेटर, मतलब वो तो इंडिकेट करती है आपने कब साइट ली है क्वेश्चन में।
राइट।
और उसमें भी मरपास, उसमें तो अपर मरपास तो मॉर्निंग में हो जाएगा ना सर? मॉर्निंग में
बेटा
अगर 3।
नंबर वन, ये अपर और लोअर मरपास इट अप्लाइज ओनली टू द साइट ऑफ द मून। इट डजेंट अप्लाई टू स्टार्स, इट डजेंट अप्लाई टू सन, और किसी बॉडी के लिए अप्लाई नहीं होता। सिर्फ मून एक ऐसी बॉडी है जिसके दो मरपास हमारे एल्मनैक में दिए हैं। तो पहली तो बात ये क्लियर हमने रखनी है, अपर एंड लोअर इन द एल्मनैक इज गिवन ओनली फॉर द मून, राइट?
यस सर।
सो ये तो क्लियर हो गया। अब तुम्हारा जो डाउट है वो एक बार मुझे फिर से बताओ।
सर डाउट ये है कि अगर जैसे उसमें क्वेश्चन में लिखा है कि एएम साइट है,
जी,
मतलब उन्होंने मॉर्निंग टाइम पे ली है, और
वेरी
मरपास में टाइमिंग लिखा हुआ एएम, मतलब 11 बजे लिखा हुआ है, जैसे मरपास अपर मरपास या लोअर जो भी है उसमें 11 बजे लिखा हुआ है, तो दैट मीन्स कि वो उस टाइम मॉर्निंग के टाइम पे वही वाला मरपास यूज हुआ होगा ना? अगर जैसे मरपास का टाइमिंग और शिप्स मीन टाइम बहुत लेट आ जाता
होल्ड
है।
ऑन बेटा, होल्ड ऑन होल्ड ऑन होल्ड ऑन। अब आप ये बोल रहे हो कि क्वेश्चन में उन्होंने हमें मून के एक्स मेरिडियन की बात कर रहे हैं हम, राइट?
हाँ जी। हाँ जी।
मून का
और
एक
वैसे
एक्स
ही क्वेश्चन
मेरिडियन
ये
का
सर
क्वेश्चन,
अमित जी का है,
होल्ड
अमित
ऑन होल्ड
कुमार
ऑन
का
होल्ड ऑन,
क्वेश्चन।
लेट मी एक्सप्लेन फर्स्ट। हमारे पास एक मून का एक्स मेरिडियन का क्वेश्चन है। उस क्वेश्चन में हमें यह बताया गया है इट इज AM ऑन द शिप। हम जाके मून के दोनों मेरिडियन पैसेज टाइम्स को चेक करते हैं, अपर भी और लोअर भी। हमें अपर मरपास जो है वो PM में मिलता है। अब बात फंस गई, गड़बड़ हो गई। मैंने आपको बोला है अपर लेना है, आप अगर अपर लोगे तो आप PM में जा रहे हो, और जो टाइम क्वेश्चन में दे रखा है वो AM है। इज दिस द डाउट?
करेक्ट सर।
दिस इज द डाउट ना? वेरी गुड। अब बेटा ऐसा कभी नहीं होगा। अगर आपको मून का एक्स मेरिडियन का क्वेश्चन दिया जाएगा, उसमें यूजुअली एएम पीएम इंडिकेशन बताई ही नहीं जाती। प्रैगनैव की बुक खोलो एंड यू कैन चेक कि एएम पीएम इंडिकेशन मोस्ट ऑफ द मून्स मरपास क्वेश्चन में नहीं होगी। अगर बताई गई है तो वो आपके अपर मरपास के टाइम के साथ मैच करेगी। अगर बताया है उन्होंने, वो हमेशा आपके अपर मरपास टाइम के साथ मैच करेगी ही। अगर नहीं मैच कर रही है तो ये क्वेश्चन गलत है।
सर मतलब हमेशा अपर मर पास ही लेना है, आपके बोलने का मतलब है सर?
यस यस बेटा यस। मून का अगर मेरिडियन पैसेज क्वेश्चन आपको आता है और उसने आपको कुछ नहीं बताया है, और कुछ नहीं बताया है, सिर्फ उसने ये बोला है दिस इज द मून एक्स मेरिडियन ऑब्जर्वेशन, तो आप हमेशा अपर मरपास ही लोगे। अब ये भी डाउट माइंड में आ सकता है कि फिर सर लोअर कब लेना है? लोअर तभी लेना है व्हेन द क्वेश्चन सेज दिस वाज द inferior meridian passage of the moon or this was the meridian passage of the moon on the observer's inferior meridian। सिर्फ तभी लोअर हमने लेना है, अदरवाइज बाकी सारे क्वेश्चन में अपर मरपास का टाइम ही लेना है। ओके बेटा, क्लियर है?
ओके सर, थैंक यू सर।
और बताओ बेटा, और कोई डाउट?
हाँ जी सर, वो ठीक है सर। वो सर जैसे वो एक क्वेश्चन भेजा था ना ग्रुप में, उसमें ऐसे लिखा हुआ था दैट 21 जुलाई AM एट शिप DR समथिंग और ट्रू ऑल्टीट्यूड ऑफ द मून ऑन द मेरिडियन बेरिंग साउथ वाज दिस। तो उसी में सर पूछ रहे थे बस, AM जैसे दिया हुआ था तो अपर ही लिया था सर उसमें।
तो उसमें बेटा मैच कर रहा होगा ये मून के अपर मरपास टाइम के साथ, इट मस्ट बी मैचिंग।
हाँ सर, मतलब उसमें वही देखा मैंने तो, उसकी लॉन्गिट्यूड वेस्ट दिया हुआ है तो GMT वेस्ट होगा, और लोकल मीन टाइम जो अपर मरपास का था वो अराउंड 5 बजे का था,
राइट राइट
तो
राइट
GMT बनेगा वो AM टाइम में ही जा रहा था, तो वही वाला होगा
राइट,
मतलब।
दैट्स
एक मिनट सर, ठीक है सर।
ऑलवेज मैच। ओके बेटा, ऑल राइट। ओके
सर
हाँ हाँ बोलो बेटा।
सर ये जो सरकमपोलर बॉडी की फिगर है, वो एक बार सर सेलेस्टियल स्फीयर पे बना के दिखा सकते हैं क्या?
सरकमपोलर बॉडी की फिगर सेलेस्टियल स्फीयर पे? ओके,
यस सर।
आई कैन ट्राई। ठीक है, थोड़ा सा समझना पड़ेगा डायग्राम में, बट आई विल ट्राई टू मेक इट। लेट मी शो यू, जस्ट गिव मी अ मिनट।
ओके सर।
ओके बेटा, अभी आप जो डायग्राम देख रहे हो इसमें लेफ्ट साइड की जो डायग्राम है दैट इज ए रैशनल सॉरी द सेलेस्टियल स्फीयर डायग्राम, करेक्ट?
यस सर।
ओके, अब बेटा आप ध्यान से देखो, इसमें जो ये पर्टिकुलर स्टार है, यू कैन सी द स्टार एट पोजीशन एक्स, राइट? दिस इज द पोल एनसीपी जहां पे लिखा है, एंड दिस इज द पोलर डिस्टेंस। मैरून कलर की जो आर्क है दैट इज द पोलर डिस्टेंस। तो ये जो स्टार है,
यस
हाउ
सर।
द स्टार इज गोइंग टू मूव? दिस स्टार इज गोइंग टू मूव इन दिस पर्टिकुलर वे। ये ऐसे मूव करेगा बेटा। कैसे मूव करेगा ये? एग्जैक्टली जैसे ये इक्विनॉक्शियल है, इसके पैरेलल ही मूव करेगा। So it will be moving like this, going up to here, then going on the other side of the diagram and coming this way. Can you visualize it beta as the cursor is moving?
सर इक्विनॉक्शियल के पैरेलल?
हाँ बेटा, सारी की सारी बॉडीज इक्विनॉक्शियल के पैरेलल ही मूव करती हैं।
यस सर।
ओके, सो ये स्टार भी इक्विनॉक्शियल के पैरेलल बिल्कुल ऐसे ही सर्कल में मूव करेगा। और ये पूरा का पूरा सर्कल जो है, इफ यू लुक केयरफुली, ऑब्जर्वर की रैशनल हॉराइजन के ऊपर बनेगा।
यस सर।
ओके, So this could be the circumpolar body shown in a celestial sphere diagram like this. अगर इसमें डिफिकल्टी हो रही है, टेक ए स्टार वेरी क्लोज टू द पोल. यहाँ पे अगर कोई स्टार ले लो वेयर माई कर्सर इज, इट विल बी मूविंग लाइक दिस.
ओके सर.
Okay, so this is how a circumpolar body would appear on the celestial sphere.
ओके सर, थैंक यू.
अब
Yes.
अगर कोई बॉडी इक्विनॉक्शियल पे है, जीरो डेक्लिनेशन है, तो वो तो इक्विनॉक्शियल पे मूव करेगी. इस पॉइंट पे जाके वो सेट कर जाएगी बिकॉज इट विल गो बिलो अवर हॉराइजन. फिर वो हमारी हॉराइजन के नीचे रहेगी एंड इस पॉइंट पे जब बॉडी पहुंचेगी ई पॉइंट पे, देन इट विल राइज एंड कम अबव अवर हॉराइजन. दिस इज ए नॉर्मल बॉडी, ए नॉन सर्कमपोलर बॉडी. राइट बेटा?
Yes sir.
Okay, good. So beta, this was about the circumpolar bodies. So we found out the conditions which a body should satisfy to become circumpolar, and then we saw how the numerical based on circumpolar bodies are solved. ये basic approach अपने mind में याद रखनी है. First make the rational horizon diagram, then put all the information in the diagram, and you will get a lead or way out from the diagram itself. So with this, we finish off the circumpolar bodies, and the session is also finished. So I'll see you in the next session.
Okay sir,
thank you.
Thank you. Bye-bye. Thanks.
Thank you, sir.
Thank you.